Okay, you can follow this on the document. Okay, and the document will be posted along with the video down in the description. It's too long to put the whole thing in there, but I'll post a link along with the videos. Okay, so what we have here is just a garden variety, small marble. And what I've done while you were gone, I've taken a really good pair of tweezers and I plucked the nuclei out of approximately 10 to the 40th I plugged neutrons out of about 10 to the 40th nuclei and put them in here. It's kind of an exhausting process. There's a significant amount of resistance when you pull a neutron out of a nucleus. You can actually feel it. Okay, well, obviously I didn't do that. But let's say that I have, and I packed this thing full of neutrons, tightly packed neutrons. You think it'd weigh more than a ton? You think it may more than 10 tons? Okay. 1,000,000 tons? Yeah, you get 1,000,000 tons easily. Okay. You would have 10 to the 11th kilograms. Okay. Which is 1,000,000,000 tons. And you would be feeling the gravitational effect of this thing. And if I was holding it this close to my head, I think it might absorb my head. Okay. But at a distance of 1 meter, I can hold this 1 meter away. I don't know what's going to happen to my fingers, but it's 1 meter away from me. I'm going to have a gravitational attraction to this thing, at least the parts of me that are 1 meter away. Going to have gravitational attraction to this thing that's approximately equal to the gravitational attraction I feel from the Earth. Okay. And that's what the first little bit here says. Now, that means that if I've got, now this is closer to 1 meter, but if this thing is to orbit, okay, now let's pretend we're in free fall. You know, this is a large elevator. It's been raised to a height of 100 miles and it's in free fall. We've got a parachute that'll save us before we crash. Got to deploy fairly early because we're going to be moving really fast. Okay, but anyhow, okay. So there are no other forces on this thing except the force of my gravitational attraction, which is negligible, and your gravitational attraction, which is even more negligible. Most of you aren't all that much bigger than I am, and you're a lot further away. Okay. So this is going to orbit. If I give it just the right velocity, I put it here and just give it the right push, it should orbit. How fast should it be orbiting? Well, if it's 1 meter away, okay, now it's maybe a little more than half a meter, but if it's 1 meter away, how fast would it be orbiting? Okay, well, the gravitational attraction of this thing from the gravitational field has a strength of 10 meters over r squared. Okay. What is that if r equals 1 meter? Just write it down, make sure you get it. I'm not going to take time to ask you to answer, but it's 10 meters over the square of 1 meter. You know, I've got the wrong units on that thing. Remember, I did this like at 1 a.m., 2 a.m. Okay, and it's treating R like it had units of time because I was being ignorant. I figured out the mass of this thing. I didn't have any trouble doing that. Just some basic stuff. It's 10 meters cubed per second squared over r squared. G of 1 meter is then 10 meters cubed per second squared over 1 meter quantity squared, which comes out 10 meters per second squared. So what we have is 10 to the 11 kilograms at distance r. We want to have the ball orbiting orbit. And incidentally, I will tell you how this machine that I use, this little thing right here, which does a pretty good AI speech to text, okay? But it does some bizarre stuff. And orbit usually comes out or with a profanity. So I've got to be careful in my editing before I distribute these things. And if I write that program, I'll try to find every bit of profanity I can and edit it out, or at least flag it. Okay. Okay, there we have it. So if I plug in 1 meter, I get 10 meter per second squared. Okay. So you might make a note there that that should be meters cubed per second squared in the numerator. If r had been in units of seconds, it would have been meters per second squared. And I was surprised when it didn't come out that way. Okay. There we have. Okay, so now what is orbital velocity? Well, what's your principle for orbital velocity? The centripetal force is supplied by gravitation. Or gravitational acceleration equals centripetal acceleration. Okay. Now I'm having a problem here. I'm going to have to pause for a second. Okay, sorry, I had to wrap my phone. In front of my handwriting. Okay, so we have gravitational acceleration equals centripetal acceleration. Gravitational field is the strength of the gravitational acceleration. And it's a centripetal force because this ball is always being pulled toward the model. Okay. So we easily solve this for B. There's one unique velocity that'll give us a circular orbit. Now, if the orbit wasn't circular, if I gave it a little too much speed, well, just pretend the massive ball is here and the steel ball is here. Give it too much speed, it's going to go way out here before it comes back. Okay. And give it too much speed, it'll just go on forever. It'll get bent, but it's going to follow a hyperbolic path as it recedes off and never comes back. So those are important ideas. Okay. Now, if R is 3 meters, okay, then we're going to set this equal to 10 meters per second squared, right? Then we multiply both sides by, what did I say? Did I say if R is 3 meters? Did I say that? If R is 1 meter. If R is 1 meter, we're going to multiply it by 10 meters per second squared and get 10 meters squared per second squared. That's going to be V squared, right? So we can do this at 1 meter. Need a longer piece of chalk. Then we get V equals square root of 10 meters per second. You can solve that equation yourself very easily. Okay. Very simple. Multiply both sides by 1 meter, you get 10 meters squared per second squared. When you take the square root, meters squared per second squared becomes meters per second, and you got the square root of 10. Okay. So kinetic energy is the mass of the ball, mass of the, that's SAT for satellite. That times 10 meters squared per second squared. Well, that R equals 2 meters. You can work it out. G of R is 2.5 meters per second squared. Something is wrong with my units. Hang on. Okay, there's nothing wrong. There's nothing was. Okay. Then your kinetic energy is mass of the satellite times what? You're going to multiply 3 meters by 10 meters per second, but by 2.5 meters per second squared. You're going to get 7.5 meters squared per second squared. So it's going to be 7.5. You're going to get less kinetic energy at 2 meters than you get at 1 meter. Okay. At 3 meters, G of R is approximately 1.1 meter per second squared. So your kinetic energy would be mass of the satellite and you're going to get about 1.1 meters squared per second squared. Check my numbers and things. Okay. The point is your kinetic energy falls off pretty rapidly as you move up. And your velocity falls off as a square root of the kinetic energy. So your velocity at 3 meters, you'd have a 1.1 meter per second squared here. You'd have a square root of 3.3 meters per second squared. And like I said, my numbers need to be checked. Okay, be 3.3, not 1.1. And the square root of 3.3 is about 1.7 meter per second. Well, actually 1.8. So your velocity is falling off. That's the point. So as your orbital distance increases, your kinetic energy decreases. Okay. Now, orbital potential energy, I'll use U for orbital for potential energy. Well, we want to figure out a reference point for the orbital potential energy. We can set the potential energy equal to 0 wherever we want to. It turns out that we set it equal to 0 at r equals infinity, at infinite separation. We could set it equal to 0 at the surface of the Earth if we're talking about satellites around the Earth. We could set it equal to 0 at the surface of that marble if it was safe to get near the surface. Okay. But infinity is the same for everything. Everything is equally distant from infinite separation from any one thing. Okay. So how do we do the orbital potential energy? Well, first of all, r equals 1 meter, r equals 2 meters. The force of gravity goes from mass of the satellite times 10 meters per second squared to a fourth of that. Okay, because in this process, we figured out the gravitational acceleration at this point. If you want the gravitational force, you just multiply the acceleration by the mass. We're talking about the mass of our satellite, which could be anything. Okay. What's the average gravitational force? Well, the gravitational force looks like this. It's a reciprocal square because of the rule, G of r is this divided by r squared. Okay. So if, let's say, r equals 1 here, then G is 10 meters per second squared. So that when r equals 2, I should have put it out a little further. This isn't to scale. This thing should be much more drastic curve. I didn't draw it very well. But when r equals 2, let's just say r equals 2 is here. We have can't read it, just says 2.5 meters per second squared. Here, what's the average? We know to get the average value of a quantity, when you have the curve, you find the line that cuts the area beneath the curve in half, okay? Between the 2 points. And that's going to be down here somewhere. Okay, well, you can think about that, but how do we get the actual average value of the force, or yeah, of the gravitational force? Okay. We would integrate from here to here. We'd integrate the force from here to here. We can integrate with respect to R. This is G of R, and then you have the mass of the satellite. Now that's getting too hard to read. Let me rewrite it. I'm sorry about my handwriting. This thumb is really messing me up. Okay. G of R is okay. Now, one thing I forgot. This is actually the work done by gravity. Okay. And the delta U would be the negative of the work done by gravity. Do this. And we plug the 1 meter and the 2 meter in. And that negative sign I put in here, I forgot to put there. That's not right. This is work done by gravity. This is equal and opposite to the work done by gravity. Well, there you have it. And there it is. Now, distance R to infinity cubed per second squared. that negative sign I put here and didn't think I wanted it again? No, I don't. Yes, I do. No, I don't. Yes, I did. I did. No. Okay, worry about the details that we're integrating the force between 2 points. That gives us the work, which is equal and opposite to the change in potential energy. Okay. When we do this integral, I want the negative sign there. And my limit on the integral is r. Should use the dummy variable. I'm going to use rho, although it has other connotations. It's the Greek. I don't have room to write it. The x would be negative here. As your antiderivative of reciprocal of y squared is negative 1 over rho. Okay, we have this. It's a change in potential energy as we go from distance r to distance infinity. That's your change in U. Okay. That U equals 0 at infinity, then sorry, I've lapsed into him. Then at distance r, the potential energy is this. Now these are all simple integrals. Simple analysis. Okay, the work you need to get from r to infinity for this g of r function that corresponds to that little green marble is this. Okay. If your satellite has a mass of 100 kilograms, then you'd have 100 kilogram. It'll be meters squared per second squared because r has units of meters, right? Divided by r, the number r's because we use the meter, which is 1,000 joules. Okay, divided by r. Now you don't have to work out that numerically. You're going to work it out symbolically probably next time. Just means that at 1 meter, you got 1,000 joules of potential energy. It'll take you 1,000 joules to send this ball off to infinity from 1 meter. I don't know what happened to my satellite. I guess it already went off to infinity. Okay, so anyhow, we got the ball, we got our satellite out here. We're gonna have to fling that ball with about 1,000 joules of energy, right? Okay. Question, can we do that? Give you one statistic. At my peak, I could throw a nice spiral football path 55 yards, which is not NFL level. It's not even really Division I college level, but it's a pretty good throw. For somebody who can't throw a baseball very far. Something about the mechanics of my shoulder. They put me in the outfield and hope I never had to throw. You can figure out how many joules of energy I was able to deliver with a pretty good arm. Okay, not good enough to brag about, but pretty good arm. All right. Then you could take these guys who can throw. My buddy, Fat Boy, could throw just short of 80. And I used to catch those passes on a lined off field. I knew where I was catching the pass and I knew where he threw it from. Pushing 80, he might have thrown a couple of 80s. How many joules could he use? Okay, just to relate 1,000 joules to something. Okay. And another alternative is 1,000 joules means I do a 50-inch vertical leap, which I couldn't come close to. Okay, unimpressive vertical leap in my case. 50 inches would be impressive. And that's the amount of energy you would have to give that, well, a mass of 100 kilograms. Okay, that's actually, I was doing the steel ball. That steel ball was 100 kilograms. Okay. You figure out how fast it would have to go to escape this thing, because that's escape velocity. Well, there's a concept. Now, what you see is you have your source here, and you have different orbits, and you have different potential energies. Okay. Potential energy might be negative 1,000 joules here, maybe negative 500 joules here, maybe negative 300 joules here. Now, is your potential energy increasing or decreasing as you go outward? Increasing or decreasing? Yeah, you go from bigger negative numbers to smaller negative numbers. You're getting closer to zero. And of course, you don't get to zero until you get out there to infinity. Make sense? Now, you already see that you can calculate the kinetic energy just by calculating your v squared over r equals whatever your gravitational acceleration is, right? Use that velocity with the mass, such as mv, 1/2 mv squared. So you can get the kinetic energy of whatever it is. Okay. And I think for 100 kilograms, you get numbers like this. Turns out, what's the change in kinetic energy? What happens to your velocity as you move out? Well, you just work out v squared over r equals something that decreases as a square of your distance, okay? And it turns out that you get less and less kinetic energy. Now, the change in potential energy is positive, change in kinetic energy is negative, but the kinetic energy itself is always positive. It can't be negative. Okay? You can't get a squared velocity that's less than zero. Anything you square is going to be positive. Kinetic energy is always positive. Change in potential energy, and the potential energy is always negative, but the change in the potential energy is always positive. Change in kinetic energy is negative. absolute value changing. Let me use U, okay. So don't mix up my symbols. Okay. Magnitude of delta U is 1/2 magnitude of delta K. Your change in potential energy is twice as great as your change in kinetic energy, but of the opposite sign. It follows U plus K is not constant. What's conservation of energy say? Conservation of energy says in the absence of non-conservative forces, U plus K has to be constant in a closed system. Consider this to be a closed system. Okay. What's that tell you? It tells you got to have non-conservative forces. So any change in the circular orbit, and I just realized I'm off the board, sorry. The thumb thing has me a little disoriented. My excuse today. Okay. U plus A is a constant. Any change in circular orbit implies work by your non-conservative force is not zero. This is why, if you want to change orbits, you carry fuel with you. Fuel burns your rocket engines, creating a non-conservative force that either increases your velocity or decreases your velocity. Okay. Now, if you're out there orbit around this planet, I'll do the orbit in this plane, so you can see orbiting around this planet like so, and you want to go to an orbit that's further away from the planet, what do you have to do?
Burn program.
You have to burn fuel, and that's what you said, and that's correct. Whoever said that, somebody in the hall. Somebody walking by knew the answer. Okay, well, you all knew it too. Okay, U plus K isn't constant. If you want to change from one circular orbit to another, what has to happen to your total energy? Well, you're going to have to increase your potential energy by twice as much as your kinetic energy decrease. Okay. So how do you increase your potential energy while you decrease your kinetic energy? Well, you do this. You're in this orbit, right? You increase your kinetic energy. You burn your fuels, let's say right here, and you go out into an elliptical orbit. In that elliptical orbit, the furthest point is at the circle you're trying to reach. The nearest point is where you burn it. Okay. Actually, yeah, if you burn it, it's probably going to do this. All right, it's going to go into elliptical orbit, one way or the other. And that elliptical orbit is going to reach the point of your circular orbit, but then it's going to fall back to the distance it started from. It'll be moving faster at that point, just as fast as it was after you burned your engines. Okay, So there's more kinetic energy in this orbit than there was in this one. But we said you want to increase your potential energy, but decrease your kinetic energy. Well, the point is that you slow down as you move further. Your potential energy is increasing automatically as you go through this elliptical orbit down to this point. Okay? So your velocity is bottomed out right here. Okay, it's at a minimum, which is less than the velocity you need for that circular orbit. So you burn your engines again when you're right here to put yourself in the circular orbit, but at a lower velocity than you had here. That's a little bit counterintuitive. That's what happens. Okay. We did have a correction. I was doing this quickly. Your kinetic energy will be 1/2 mv squared. Your v squared would of course be 10 meters squared per second squared, but half of that would be this. Okay. If this was 2.5 meters per second squared and this was 2 meters, I'd double that and get 5 meters, right? Not 5 meters squared per second squared, so they'd be the square root of 5 meters squared per second squared. So I think, and this is where the objection was, they said, shouldn't that be 5 meters squared per second squared? Yes, it should. Okay. Now, if you got 1.1 meters squared per second squared and 3.3 meters down here, you're going to get the square root of 3.3 meters squared per second squared. 1/2 mv squared would divide that by 2. Okay. So thank you. But again, all these calculations, really trying to give a broad sweep and not worry about the details of the calculations, because they can always be corrected. Okay. The whole point of this is just that in doing this kind of analysis, and we will do it symbolically next time, we get expressions for the potential energy. Okay. We have expressions for the potential energy. It turns out that the magnitude of the change in potential energy is half the magnitude of the change in kinetic energy. And we have an energy profile that looks something like this. Okay, we got potential energies, we have kinetic energies. Now I'm using the specific mass of the satellite to get these energies. I haven't done that for the kinetic energy, but if we did write it out, we would see that these changes are half as great as these changes. Okay. And since the kinetic and potential energies are changing differently, the sum of kinetic and potential can't be constant, which is your evidence that you got to carry fuel if you want to change your orbit. Then I just described with some hand waving how you change it. If you're in a circular orbit, you burn, go into an elliptical orbit. Okay, where the elliptical orbit takes you out to the circle you want to be on. And then when you get to there, you burn again so you can stay on the circle. It's a transfer orbit. Okay. And that's kind of cool. Think about it, especially when you work it out with symbols and see what's really going on. Okay, the next part here is on angular momentum, and I don't want to get into that because I do want to continue the main theme, which is the importance of the potential energy function. Okay. You see that in this case, we get a potential energy function. Okay. And that potential energy function governs what goes on in this system, in a sense. We're going to see a little bit more about that and make a little more sense out of that statement. Not going to talk about the angular momentum stuff right now, but on some of the homework I've seen, a little bit I've gotten, we'll do an R cross F to get the torque. And the R has an I on it, and the F has a J on it, I vector, J vector. And then the cross product doesn't have any vector indication at all. I cross J is K. So you got to know where that angular momentum is to understand how angular momentum behaves. Okay, so make sure you do the vectors. And also symbolically, it doesn't take long to put an arrow over something that's a vector. Either that or figure out how to handwrite in boldface. Get a big old Sharpie, you know. You don't want to do that. Just put an arrow over it, that's quicker. Okay, you want to keep track of the type of the thing you're doing. It's just bookkeeping that becomes important, especially if you make an error. Okay, you go back and say, oh man, that was a vector. I treated it like it was a scale. Okay, easy to do. And something I expect I'm going to see more of because you're just getting used to the whole thing. All right, so make sure you keep track of the vector nature of angular velocity, angular acceleration, angular momentum. That's key. We'll talk more about it next time. Now I want to talk about potential energy functions. We know that the potential energy function at the bottom of this third page or fourth page, third page probably, maybe the fourth, says the potential energy function is negative integral of conservative force with respect to position. Okay, I don't necessarily like that with respect to terminology, and I'm probably going to change that terminology a little bit. But you've got your force and your dx or dy or dr or whatever is your position. Okay, it follows from that that the conservative force is the derivative of your potential energy function. Okay, so that's a big deal. And we want to make sure we understand that. And I give you several examples. So let's just say x is your variable. Derivative of u of x with respect to x equals the force at x. And that for the conservative force at x. Okay, examples. And it's negative du dx. You can work out why that is. Okay. Okay, we're going to use x for the position at which I get the conservative force. So I do the negative of the integral. I'm sorry, the equal and opposite to the work done by the conservative force, the potential energy at x, is negative the integral of the force with respect to x. Okay, except I can't use x here because I want x to be where I'm integrating to. So I use the Greek psi, which is corresponding to x as a dummy variable. Okay, and you should have seen that in calculus. So, you know, look it up. It's just what I use here because I don't want to use x. But I'm integrating this expression. Anyhow, that's 1/2 kx squared. Now, no surprise. I'll use the prime for the derivative, where it's clear that the prime is derivative with respect to x. And that derivative is negative kx. So we've come a full circle. Make sure you understand that full circle. It always works. Okay? Let's try something else. MGY. I don't like H. Gonna use Y for vertical position. Okay? That is a valid expression for potential energy in a constant gravitational field. Okay? Where Y is your position parallel to the gravitational field. Okay? That's gravity near the planet. That's a force of gravity. Okay? Take the derivative of U equal force. In the example we just did, if I integrate this from R to infinity, I get negative 10 meters cubed per second squared over R. I don't think I ever did that over there. I thought I had. Anyhow, we do. So what's du dr? I've actually got a sign change wrong, and my signs over there are a little bit messed up. We'll sort that out when we do the thing with the full expression, so we don't have to mess with numbers and units. Because it actually is neater if we don't have to mess with the numbers and the units. Okay? It's just showing you kind of the flow of the ideas. And there is a mistake in my signs. Because actually this force ought to be negative. Yes. And if I put a negative here, the rest of this actually kind of follows this. Well, I'm not gonna do it. Okay. We'll work a little bit more out about that. My point is that in every case, if you take the derivative of the potential energy with respect to this variable, you're going to get the force. Okay. And if you integrate the force, you're going to get the potential energy in its full circle. It's applicable to things that we've seen in lab. You know, the correlation between force and potential energy changes. Okay. Okay. I think about here on the fourth page, we get in the absence of non-conservative forces, change in kinetic energy and the change in potential energy are going to be equal and opposite. That's because the total mechanical energy, have you seen that term? If you've read your text, you've seen the term, but the total mechanical energy is just U plus K. Sum of your potential and kinetic energy. That's how much energy you've got to deal with, okay? If you don't do anything else. Of course, friction's gonna do work. It's a non-conservative force, and it's gonna decrease your total mechanical energy. We set the beam in oscillation. The amplitude keeps decreasing, although it keeps going for quite a while because the friction is pretty low, but you have a frictional torque. It's doing work against the system. The direction of motion of the system is opposite to the direction in which the torque, in which the frictional force acts. So you're decreasing the mechanical energy of the system. And there are several statements here that you maybe want to digest. I could read them to you. I mean, if non-conservative forces do positive work, then the total mechanical energy increases. Example of that, here's your orbit, okay? Or here's your orbit. And we do some positive work and we go into this elliptical orbit. Okay? Total mechanical energy stays the same now in that elliptical orbit after we've added our energy, okay? After the impulsive force times time interval gives you the change in momentum, okay? And we get down here and we're going too slow now. Although we're at the right distance for the orbit, we've got to add more energy. So we've got to add more work by non-conservative forces, namely our rocket engine forces. Okay. In the case I just mentioned with the oscillating beam, your total mechanical energy decreases. Potential energy decreases, your kinetic energy decreases. Okay. Well, actually, your kinetic and potential energy keep exchanging themselves, but over smaller and smaller limits. Okay, there's several statements there that are worth thinking about. Just gives you a conceptual idea about what's going on here, because the equations are really pretty easy to deal with once you have the concepts. Okay. Yeah, and you know, the other example of a potential energy function potential energy of the oscillating beam is one half u k theta squared, just like one half kx squared. Negative du d theta is negative k theta, which is your restoring torque. If you integrate this, you get this. If you differentiate this, you get this. There's a graphical interpretation of that that I'm not going to attempt to show you today, but I will next time. I have a statement that if you know for a pendulum or an oscillating beam, a simple harmonic motion in either case well, let me flesh this out a little bit. Okay, so you've got let's say it's a pendulum. Okay. Get down with you from position XI to position XF is this. Okay. Get something like this. In other words, delta K equals negative delta U. For an ideal pendulum, your mechanical energy is conserved. So if this decreases, this increases by the same amount. So if you know how fast the thing was going initially, and you know where you want it to stop and where you want to observe it, you figure out the change in potential energy. That's going to be equal and opposite to the change in kinetic energy. So you know all this and this to be able to find this. Now, with pendulum, the other thing you can do is you have the equation of motion, one form. Now, something I asked you to do almost 2 weeks ago was verify that this equation satisfies the differential equation where acceleration is equal to negative kx. So that comes from satisfies. You take differential equations and you see this on the test, it's going to be something you leap for joy about because that's one of the simplest second order equations you could ever see, isn't it? Okay. Use your e to the I t, okay, as a trial function. Get your complex eigenvalues, it turns out, and go from there and you come up with this. Okay. That's very simple and very fundamental if you know a little trigonometry and stuff. Okay, well, there's your equation of motion. So B and A just come directly from this, right? What's omega? Omega is the square root of K over M. And now, of course, if you know this, you're never going to be tempted to use the equations of uniformly accelerated motion for a pendulum. They don't apply. It's the worst thing you could do. I penalize it heavily on an exam. Okay. Okay. And you can draw the same conclusion here using these equations. And that's going to be one of your transition problems. Okay. Now, my final statement on here is that in the context of changing orbits, it says free fall just doesn't cut it when trying to change orbits. Because free fall, you retain your mechanical energy, assuming there's no atmosphere to slow you down. I have some stuff in here about, well, okay. One thing you really kind of want to carry away here is just this relationship between potential energy and force. Okay. You can see this pendulum as a system in which the potential energy constantly changes. Or you can see it as a system governed by these equations, and you want to be able to pull it together. And I've got some problems to give you 4 formulas that you can use, nothing else except concepts to do that, okay? And there'll be some other problems. They'll get posted this afternoon. There's probably 6 or 7 of them, but they're not all going to be assigned right away. Okay, some of them maybe you're still a little uncertain that they completely make sense. All right. Okay. So, read what's on here, see if it makes more sense to you than it would have if we hadn't done the examples.